All right, so let's dive into some of this phishing detection research.
Yeah, it's a fascinating paper, tackling this problem of
Sure.
machine learning models
hmm
becoming obsolete as quickly as the techniques evolve to get around them.
It feels like every time we come up with something new, the bad guys are one step ahead.
Yeah, and that's the problem this paper addresses head on.
Okay.
Traditional machine learning models, they struggle with this dynamic nature of these phishing attacks.
Right.
And to put the scale of this problem into perspective,
Yeah.
the Anti-Phishing Working Group reported a record 316,747 phishing attacks in a single month
Wow.
back in December 2021.
That's a massive number.
That's a huge number, and with web development
Yeah.
and these techniques constantly in flux, the features our models rely on keep changing,
Yeah.
making them less effective over time.
So how do they propose we tackle this challenge?
Well, the paper explores continual learning.
Okay.
And so imagine a model that can adapt to new data without forgetting its past knowledge.
Right.
That's the essence of continual learning.
That sounds promising, but can you elaborate on the specific techniques they use?
Sure, so the paper focuses on two prominent techniques:
Oh,
learning without forgetting, or LWF, and elastic weight consolidation, or EWC.
yeah?
LWF cleverly stabilizes the model's output on old tasks, even as it learns from new data.
Interesting.
It achieves this by preventing significant changes to the weights
Okay.
that are critical for previously acquired knowledge.
That's clever. So it's like selectively updating the model's memory to retain important information while incorporating new learnings.
Exactly, and EWC takes a slightly different approach.
Okay.
It identifies shared feature spaces between old and new tasks and penalizes changes to weights essential for past tasks.
Interesting. So both methods aim to preserve the model's ability to detect old phishing techniques while allowing it to adapt to new ones.
Exactly, and they tested these techniques against a vanilla neural network, which represents the traditional approach, and a transfer learning model, where a pre-trained model is fine-tuned on new data.
That's a good way to benchmark the performance of continual learning methods.
Right, and they meticulously evaluated these models
Okay.
using phishing and benign website samples collected over 3 years from 2018 to 2020,
Okay.
divided into 6 distinct data sets.
Okay.
Each data set represents a snapshot of the phishing landscape at a different point in time.
And this setup really allows them to test how well each approach adapts to the evolving nature of phishing attacks.
Absolutely. It's a very clever experimental design
Yeah.
that goes beyond simply measuring accuracy on a single data set.
Right.
It provides a much more nuanced view of how these models perform over time as the phishing landscape changes.
I'm curious to see how the different approaches performed. Did the continual learning methods live up to the hype?
Well, as you might expect, the vanilla neural network performs well on the specific data set it was trained on, but struggles when faced with newer data sets.
Yeah.
And this clearly demonstrates the limitations of a static model in a dynamic environment. The transfer learning model showed some improvement over the vanilla network, but it still experienced performance degradation on the original tasks as it learned new ones.
So even with a head start, traditional transfer learning couldn't fully overcome the challenge of retaining knowledge while adapting to new information.
Right, this phenomenon known as catastrophic forgetting highlights a key weakness of traditional transfer learning approaches.
So it seems like neither the vanilla neural network nor the transfer learning model could effectively handle the evolving nature of phishing attacks.
That's correct, however. Both LWF and EWC consistently outperformed the other methods.
Okay.
They maintained high accuracy on both old and new data sets, demonstrating their ability to adapt without losing previously acquired knowledge.
So it seems continual learning approaches offer a significant advantage in this context.
Precisely. By preserving knowledge while adapting to new data,
Right.
both LWF and EWC achieved significantly higher accuracy
Okay.
on all data sets compared to both the vanilla neural network and the transfer learning model.
That's a powerful demonstration of the potential of continual learning in this domain.
Yeah.
This sets the stage for some insightful findings, I'm sure.
Right.
Can you walk us through some of the key observations and results from the paper?
Absolutely. Let's delve into the specifics of their findings in the next part of our deep dive.
So we've established that continual learning shows real promise in tackling the evolving nature of phishing attacks. Can you elaborate on the specific results the researchers obtained?
Absolutely. One of the most striking findings is how the performance of the vanilla neural network, our baseline, deteriorated as it encountered newer data sets. Its accuracy on the initial data set plummeted to around 75% after just 5 retraining iterations.
Wow, that's a significant drop.
Yeah.
It highlights how a static model, even when retrained, struggles to keep up with a shifting threat landscape.
Right, and while the transfer learning model fared slightly better initially, it too fell victim to catastrophic forgetting as it was trained on new datasets. Its performance on older tasks declined.
So even with a head start, traditional transfer learning couldn't fully overcome the challenge of retaining knowledge while adapting to new information.
That's the crucial takeaway now. In stark contrast, both LWF and EWC maintained accuracy above 90% on the initial dataset, even after being trained on all subsequent datasets.
That's impressive. It suggests that continual learning methods can retain and apply previously learned knowledge effectively.
Precisely, the paper's graphs and figures beautifully illustrate this point. The visual representation of the results really brings home the difference in performance between the approaches.
It seems like they didn't just rely on numerical results, but also took care to present their findings in a way that's easy to grasp.
Yes, and this visual clarity really strengthens their argument. They also took a unique approach to feature representation, opting for deep feature representation over handcrafted features.
Can you explain why that choice is significant?
Certainly, instead of manually selecting specific features, they used embedding techniques to convert the entire HTML content of each website into a dense numerical vector. This vector acts as a unique fingerprint, capturing the essence of the website's code and structure.
So they essentially let the model learn its own features from the raw data instead of imposing predefined features.
Exactly. This approach has a distinct advantage. It captures a much richer, more nuanced set of features than any human could identify manually as a result. The model can discern subtle patterns and become more robust to variations in phishing techniques.
I see. By letting the model discover the relevant features itself, they've essentially empowered it to adapt more effectively.
Precisely, the paper specifically mentions using the FastText model for this embedding process.
What makes fast text suitable for this task?
FastText stands out for a couple of reasons. It's pre-trained on a massive data set of web pages, making it particularly adept at understanding the language and structure of websites. Furthermore, it produces embedding vectors that strike a good balance between size and information content, meaning it captures a lot of detail without making the model overly complex.
It sounds like they made a deliberate choice to use a model that's well-suited for analyzing the kind of data they're working with.
Absolutely. And while the paper goes into the specifics of their neural network architecture, the key takeaway is that it was designed to process these rich embedding vectors effectively and learn the intricate patterns that distinguish phishing websites from benign ones.
So it seems they addressed various aspects, from the choice of continual learning techniques to the feature representation method, ensuring a comprehensive approach.
Exactly, however. As with any new approach, continual learning comes with its own set of challenges.
Can you elaborate on the limitations they highlighted?
One of the primary concerns is the increasing complexity of the models as new tasks are introduced. Managing and training a model that continuously integrates new information can become increasingly difficult.
So there's a trade-off between adaptability and manageability.
That's right. And even with sophisticated techniques like LWF and EWC, the risk of catastrophic forgetting, though mitigated, isn't entirely eliminated. Further research is needed to explore more robust solutions.
I see. So while LWF and EWC address catastrophic forgetting to a significant extent, it remains an open challenge.
Indeed. And there's also the potential for data bias, where the model might become overly focused on the most recently learned tasks, potentially skewing its performance.
So ensuring balanced and representative training data becomes even more crucial in a continual learning scenario.
Absolutely. It's about striking a delicate balance between adapting to new information and preserving the model's ability to generalize across all encountered tasks.
These are certainly important considerations. However, even with these limitations, the findings presented in the paper are quite compelling. The results clearly show that continual learning offers a significant advantage over traditional approaches for tackling the dynamic nature of phishing detection.
I agree. The potential of continual learning extends beyond phishing detection. Think of other cybersecurity domains like malware detection, intrusion detection, or spam filtering, where the threat landscape constantly evolves. Continual learning offers a promising avenue for developing more robust and adaptive security systems in these areas.
That's an exciting prospect. By embracing continual learning, we can move towards a more proactive and dynamic security posture.
Indeed. Now, while we've explored the nuances of this research, it's beneficial to distill the key takeaways. Shall we move on to summarizing the essential points for our listeners?
Okay, so we've explored a lot here with continual learning and its use in phishing detection.
Yeah.
Time to bring it all together and highlight the core findings for our listeners.
Absolutely. Let's kind of crystallize this research and really pull out the most valuable insights.
First and foremost, the paper clearly shows the shortcomings of traditional machine learning models
Right.
in dealing with this constantly changing landscape of phishing attacks.
Yeah. Static models, even when retrained, they just struggle to keep pace
Right.
with these evolving tactics that cybercriminals use.
And this point is really driven home by that significant performance drop
Right.
we saw in the vanilla neural network
Exactly.
as it encountered these newer data sets.
And while transfer learning offers some initial improvement,
Yeah.
ultimately it suffers from catastrophic forgetting, highlighting its limitations in preserving that previously learned knowledge.
The research really shows that simply retraining or fine-tuning these existing models
Yeah,
isn't enough.
you need a more sophisticated approach.
Right. We need continual learning.
And that's where continual learning comes in.
The paper's key contribution is showcasing the effectiveness of these two techniques, LWF and EWC, in allowing these models to adapt to new techniques without losing the ability to detect the old ones.
Exactly. Both LWF and EWC consistently outperform the baseline vanilla neural network
Right.
and the transfer learning model, achieving significantly higher accuracy across all data sets.
This really highlights the ability of those continual learning methods to retain and apply that previously learned knowledge,
Right.
even when facing this evolving data.
The researchers took a unique approach to feature representation as well,
Yeah.
by leveraging deep feature representation instead of relying on those handcrafted features.
And this decision to allow the model to learn its own features
Right.
from the raw data proved very beneficial,
Yeah.
leading to a more robust and adaptable model.
Exactly. Using those embedding techniques, they capture a much richer and more nuanced set of features,
Right.
enabling the model to discern subtle patterns and adapt more effectively to those variations.
And they chose fast text for this embedding process,
Yeah.
which is well suited for understanding the language and structure of websites.
And their neural network architecture was designed to process these rich embedding vectors
Right.
and to learn those complex patterns that help differentiate between those phishing and benign websites.
The paper does acknowledge those challenges associated with continual learning, though,
It does.
such as model complexity, the risk of catastrophic forgetting,
Uh-huh.
and data bias.
These are all considerations for sure.
These are all considerations that need further research.
Yeah.
But the overall message is pretty clear. Continual learning offers a very promising pathway
Yes.
for more resilient and adaptive security systems.
Absolutely. Embracing continual learning allows us to move towards a more proactive security posture,
Right.
where our systems learn and adapt to stay ahead of the curve.
This research really offers this compelling vision of the future of cybersecurity,
It does.
where our defenses aren't static, but evolve as the threat landscape changes.
Couldn't have said it better myself.
It's a fascinating field with immense potential.
It is.
This paper focused on phishing detection, but these principles
Yeah.
can be applied to many other cybersecurity challenges,
Absolutely.
really paving the way for a new era of intelligent and adaptive security.
It really is exciting.
Well, we've covered all the key takeaways from this insightful paper.
We have.
For our listeners that are eager to delve a bit deeper, be sure to check out the show notes for links to the original research and any additional resources.
Yeah, keep exploring, stay curious, and until next time, stay safe in this ever-evolving digital world.